So in our math lab, we saw two shapes of exponential graphs, those that swoop up and those that swoop down. And so instead of looking at these ones like they use A's and gets a little confusing, we'll do actual examples here. So if you have an exponential function where the base is bigger than 1, like y equals 3 to the x, you will always have the point 0, 1 on your graph. You will always have an asymptote at y equals 0. And when you plug in 1 for x, you would have 1, 3. You could find other points, like I could plug in 2, and 3 squared is 9, so I could label 2, 9. But the key points that you'll label are 0, 1, and 1, whatever the base is, because that's what happens when you plug in 1 for x. So if the base is bigger than 1, you would have 0, 1, and in this case 1, 3. This graph, exponential graph, would swoop upwards, increase from left to right. And if your base was between 0 and 1, like we have with 1/5, I would have the point 1, 1/5, and that would make it swoop down. You still have 0, 1, and you still have an asymptote at y equals 0. So one of the things we need to do with our equations is be able to graph these by hand. So this question says graph y equals 1/3 x. So we recognize it as an exponential graph. We have an asymptote at y equals 0. We have the point 0, 1, and when I plug in 1 in this case, I would get 1, 1/3, so I know that this one swoops down or decreases as it goes towards the asymptote. So now we can do a little bit of an analysis of the properties that's what they're asking for us in part B. What happens to the y values each time your x values increase by 1? So we go from 0 to 1, we went from 1 to 1/3. From 1 to 2, we would go from 1/3 to 1/9. An exponential function, in this case, your y value is being multiplied by 1/3. And that's what an exponential function does. It keeps multiplying by the same value over and over and over again. Is this one increasing or decreasing? Well, now that we've drawn it, we can see that it's decreasing. It's going down from left to right. There is a y-intercept of 1, but there are no x-intercepts. The equation of the asymptote, a horizontal asymptote, is always y equals. So we have y equals 0. And when we look at the domain and range of this function, the domain is everything. There's no non-permissible values in an exponential function. The range, there's an asymptote at 0. Y is bigger than 0, but not equal to 0 because of that asymptote. So one of the things that we're going to do with our exponential graphs is the basic graph like we see here, the 1/3 x, that's considered a parent graph. Just like we had in transformations, we knew a certain number of graphs. We didn't include exponentials then, we could have. but you can do all the transformations with any exponential graph. What do you need to know for doing transformations? You need to know what the original graph looks like, and then do your stretches, compressions, and translations after that. So if you want to just turn the page, and on the side of the next page on 346, we're going to add an example, and we're going to graph, and this will be a review of our very first unit, -5 times 3 to the 2x plus 4 minus 7. So first of all, we have to recognize this as an exponential graph. That's fairly easy to see because the x is in an exponent. So we have to break this down and decide, what did the parent graph look like? What is the original graph will be y equals something to the x. What's the base of that graph that we have? That's the first thing we have to decide. Can you see that that graph has a base of 3? In fact, the exponent, which I'm going to highlight here in green, there's the exponent. That exponent is 3 to that exponent. Correct? And so off to the side, we'll quickly draw a sketch of 3 to the x. We've learned that exponential graphs always have an asymptote at y equals 0, and their key points are 0, 1. And since it's a 3 to the x, oops, that's not exactly where I want to put it, I would have 1, 3. And this one swoops up, increases, and looks like that. So my parent function is a 3 to the x. If I look at the original thing that I want to graph, what I'm going to do is I'm going to put a green box around the 3 and the x. And this is one of the reasons we saved this for this unit and not put it in the transformations unit at the beginning, is because exponential functions, part of the parent graph has a number. And that number sometimes can cause us confusion. Because if I go from left to right and describe things as I go, I have a negative. We have to ask ourselves, going back to our first unit, is that negative inside or outside the function? Is that going to be a vertical reflection or a horizontal reflection? Okay? When we talk about things being inside the function is wherever the x was originally. So wherever the x was originally is the exponent. And I strategically highlighted my entire exponent in green before to help you see that that entire exponent, that's going to be all of your horizontal translations. So when I look at that negative is not in the exponent, it's outside the function. That's going to be a vertical reflection. The 5 is going to be a vertical stretch. We would multiply our y values together. We could do both of those things and say multiply your y values by -5. The 3, this is where things got tricky because you might want to say, ooh, I want to multiply my y values by 15. Or maybe I should do something with the 3. I also want to multiply my y values by 3. No, that 3 was part of your original function. It's not a transformation. So what makes exponentials a little bit difficult is we've got a number that was in the original graph, and you might be tempted to make that a transformation. Going from left to right, the next thing we run into is this 2. This will be a horizontal compression. You would multiply your x values, remember this, by 1/2. Always do the reciprocal of horizontal. Very nice that this question was already in factored form. So this 4 is a horizontal translation. 4 right or 4 left? 4 to the left because it's a plus 4. So another reminder of our first chapter, everything that was horizontal is kind of the opposite of what your gut would think. You see the 2, but you multiply by half. You see the plus 4, but you go 4 to the left. And finally, the minus 7, that's outside of the function again. And everything outside is exactly how you would think. So the 5, you multiply by 5. The minus 7, we go down by 7. And our technique for graphing these will go right back to the same technique that we did in Chapter 3. You take some key points. So what are the points that we had on our original graph? 0, 1, 1, 3. And you think about your asymptote, but we'll do the points first. Do your stretches and compressions first, then your translations. Do you remember doing this? That was like February. You remember February? That's when it was cold. Oh, it's still cold. Sorry. Okay? So we're going to multiply stretches and compressions first. You're going to multiply your y values by -5, your x values by 1/2. Wow, that is dyslexic for today. We'll just leave that. I don't know if I've ever done that. Well, as always. All those copy maths out there that did that, you know, I'm just checking. Okay? Then what are we going to do? Our translations next, so we need to go 4 to the left and 7 down. So we can do our transformations. If I multiply my x by 1/2, this would be 0. This would be 1/2. If I multiply y by -5, this will be -5. This will be -15. 4 to the left, I'm going to be at -4 and -3.5. 7 down, -12 and -22. After you've finished your 2 points, what's going to happen to your asymptote? Well, since your asymptote's at 0, and it's a y equals, only things that change the y are going to change your asymptote. But 0 multiplied by -5 has no effect. The only thing that's going to affect it is if it gets moved up and down. It goes down 7, so my new asymptote is at -7. So there's a little review of transformations. When we go to graph, start with your asymptote. Draw a dotted line with your red pen at y equals -7. Plot the 2 new points. We have -4, -12. Okay. -4, -12, and -3.5, -22. So if this is 10, another 10 would be about here. Now with those 2 points, we still need to have the proper shape of an exponential graph, which needs to approach our asymptote. If I join those 2 points, can you see that approaching the asymptote would have to go this way? And using our transformations, we have just graphed a very complicated looking equation quite easily. We know what the parent graph looks like. We know what the transformations do to those points. The shape stays the same. Basically, it's been stretched and compressed a little bit. Still has an asymptote, and we've got our new graph. All right, questions for practice? Try 3, 5, and 7.